Oh, yes. Hello, camera people. Sweet. Yes, it's good to see you. We're back. It's week 11. We've got, like one more week left. We're so close to the end. It's really incredible. So today we're going to do some material on triple integrals. I'm going to try and use the projector. We'll see how well that works using the projector in this room, because the setup isn't totally ideal, but that's okay. Send that to the projector, get that going. Okay, so what are triple integrals? So triple integrals are double integrals, but more. We keep applying the same process of integration. So at the end of last lecture, we saw an example of calculating the volume of a box. Now I want to do a slightly more difficult example. Okay, so now we'll integrate x squared over this volume. Okay, so we've got 3 layers of integrals, and when we're evaluating these things, we work from inside out. So we start, when we're evaluating, we work from the first integral outwards. Okay, so let's see what we get there. Okay, when we integrate x squared, we'll get a third x cubed from 0 to 3 dy dz. Okay, so our first move is to integrate in x. Okay, now when we do the fundamental theorem of calculus here, we plug in this 3. That'll give us 27. We divide by 3. That'll give us 9. All right, now we integrate the next pair of variables, or sorry, the next variable. We plug that stuff into the inner parts of our integral, apply fundamental theorem, we get 18 dz. And that will evaluate to 18z. And we get here. Yes?
Is there any way to visualize what this means with the triple integral?
Oh, yeah. Good question. Okay, so yeah, what's this thing measuring is what you're asking. There's a little blackboard space. That's okay. We'll work with it. Okay, so one answer to the question, what does it mean, is we could imagine this as being the graph of some three-variable function. Okay, so the graph of a three-variable function lives in 4D. Okay, so we could think of this as being the volume under a 4D graph. Okay, sometimes people call volume of 4D things a hypervolume. I think that sounds cheesy, but sometimes people call it a hypervolume because it's a four-dimensional thing. So there's that interpretation of what this measures. Later on in the lecture, we're going to see some physical interpretations of what this could mean that are a little bit more down to earth. Okay, so if we think of the graph of a three-variable function that's in 4D, we integrate and we get the volume under the graph. That's one way of interpreting these things. Okay. Oh, yes? Okay. Yeah? We're good? All right. Okay. So that's the notion of a triple integral. These kinds of things require, like everything else in math, they require a little bit of practice. So I want to give you guys something to try out. Okay, so take maybe, let's say 3 minutes, 5 minutes, and try and work through this, talking with your next door neighbor a little bit maybe. So try and set up this integral, calculate it, and then we'll take it up in 5 minutes. Okay, very good. So let's go through the calculation. If you've still got a couple steps, that's okay. So let's see how this thing looks. So we're going to start off. Our first integral that we want to calculate is the guy in x. Right, so when we're evaluating, we work from inside out. And now we need an antiderivative for this in x. So we need something whose derivative in x is y e to the negative xy. So if we take this guy, negative e to the negative xy, when we take the derivative of this, we'll get a negative y that comes down and cancels that negative there. Okay, so we'll get the y e to the negative xy we're looking for. I guess the integration technique there is substitution. We're substituting the variable u is equal to negative x times y, I think. Okay, so we're here. Now we plug in and apply the fundamental theorem of calculus. And we're plugging in for x. Okay, so we get this expression. Which we could write like that. Now we want to integrate in y. Okay, so we get the following expression. Is everyone okay with that so far? Yeah? All right. We're using a lot of single variable integration stuff very quickly, so I just want to double check. Okay, so now we apply fundamental theorem again, and we get dz. Okay, notice that this will evaluate out to 1. So this and this will cancel. Once we've got that cancellation, we're just looking at e to the negative 1. So our final answer should be e to the negative 1. Okay, did anyone else get a different answer there? Okay, so we keep following through with this idea of integrate variable by variable. Always working from the inside of the expression out. Okay. Very good. Okay, so now I'd like to talk, the difficulty with 3 variable integrals is usually in the setup. Usually it's quite hard to understand the region of integration for these problems. Okay, so when we have a triple integral, we write the region R underneath the integral signs, and the variable of integration that we usually put here is capital V for volume. Okay, so we're integrating with respect to volume. Okay, so I want to start off this example by trying to draw what that looks like, and then we'll use the computer to check our work. Okay, so we need to develop the skills to draw regions in 3-dimensional space. Okay, so let's draw the thing. Okay, so we're going to start with the bounds on x and y. right? These are somewhat straightforward bounds. We're going between x is equal to 0 and x is equal to pi. Okay, so we've got these two lines here. With constant x coordinate. And then we've got two more lines. Y is equal to 0. Y is equal to 1. Okay, and now the hard condition to draw is this last one. Okay, so we've drawn in pink the first condition, in green the second condition, and then it's this last one that's somewhat difficult to visualize what's going on. So it's saying that z, the height of this thing, is always bounded by the x coordinate. Okay, so when we look at our graph, we know that z is going to be bigger than z is equal to 0. Right? That's that plane there. And as x gets bigger, z's going to get bigger. Okay, so when we think of this thing, the x coordinate's running here towards us, kind of coming out of the picture. And z is going to be underneath, or like bounded by that coordinate. Okay, so that'll look like sort of, how should I say this? Sort of a slanted roof coming up out of the picture. Okay, so let's try and draw that in. Okay, so the highest that z can be is when x is equal to pi, right? X is equal to pi, that's the biggest z could possibly be. And then we have this kind of slanting roof that goes down. Okay, it's hard to draw these 3D things. So it's helpful to label all the points of intersection that you can, basically, to really understand the shape of the thing. So here, where the green and pink line meet, that will be pi 1, 0. The point above that will be where z is equal to x. So that will be pi 1, pi. Over here, we've got pi 0, 0. And here we've got pi 0, pi. Okay. All right, so there's our sketch of the region of integration. I want to now try it out on the computer so that we can see sort of in 3D what that region looks like. Before we go on to the computer demo, are there questions so far? Yes? Yes, yeah. Fubini will work here too. Yeah, we will get to that in a couple examples. But yes, there is change of order Fubini theorem. Yeah, nice. Thinking ahead. Okay, so let's try this out. Geoge. Okay, so let's plot the planes. Can I put in a less than or equal to sign? That'd be cool. Whoa! Okay, hooray. So there's pi, and it has drawn nothing. All right, well, that's modern technology for you. All right, there we go. Boom. Okay, so there are the two bounds on x. If we look at them parallel, we get those two bounds there. Okay, now for the y coordinates, we've got 0 is equal to y. 1 is equal to y. Okay, so that sort of boxes things off. Notice that our region looks really huge, right? We care about this region in here, the region between 0 and 1 this way, and then 0 and pi the other way. Okay, but right now it's sort of infinitely tall. So now we add in our condition z is equal to x. Okay, and now we have to find the right angle on the thing. Maybe change some of these colors. Ooh, that's an ugly color. Okay, so I think these guys are making it harder than it looks like. So there is, in that triangle there, inside this triangle is the sloped roof that we're looking for. Okay, this line here is our condition z is equal to x. And when we kind of look inside, we see that sloped roof shape that we're looking for. Okay? The biggest value that it takes on is about 3. Right? So it's about pi. Okay, so the sloped roof is coming at us like this. Okay, are there questions or thoughts so far? Yeah, these visuals are a little hard to follow, but I think if you rotate it around, you get a sense for this thing looks like a wedge, like our diagram. Okay, so we'll come back to that in a little bit. We'll do some more graphing in a little bit. Now I want to set up this integral. Okay, so there's our last condition. Now I want to set up the integral, and we're free to choose the order here. We're free to choose how we want to write down dv. Okay, so I'll set this thing up. So it will be something like this. Okay, as we have these nice bounds here, these two bounds give us a rectangle of sorts. So let's use those bounds and say that we go from 0 to 1 in dy, 0 to pi in dx. Okay, so that's set. So we have to put them so that the order matches, right? So that the y bounds happen with dy, the x bounds happen with dx, and then our last bound is from 0 to x dz. Yes? Just because, right, so yeah, why did I choose that particular order? Just because we have this kind of nice rectangular thing happening in x and y, right? So I've got this kind of rectangle that's easy to write down here, and then I'm going to integrate out my z guy. That's the only reason I chose that order, is to put the sort of the rectangular part outside or at the end. Is that the order I picked in the notes? Okay, yeah, almost the exact same order. Okay, so now we integrate this guy. Good. Here we have to integrate in z. Okay, sine x is constant with respect to z. So when we integrate it, we pick up a coefficient here, z. Okay. Now when we evaluate, we get this guy. Okay. And now we have a tricky integral to work with. Okay, so this is an integral that requires a little bit of doing. Okay. So I'm going to skip over the exact details of how to integrate this. The tool that we use here is integration by parts. Okay, so if we take the derivative of this guy, right, we'll get a cos. So if we take the derivative of this guy, we'll get a cos, and then we have a product rule happening here. The first term will produce a cos, and the second term will produce a negative sine. Okay, so we'll wind up getting the x sine x we need, and the integration step there integration by parts. Okay, now we plug in our bounds. Okay, and we get sine of pi is 0 minus, we are still in one more level of integral. Okay, so we get sine of pi is 0, cos of pi is -1. All of this stuff is 0, so we get the whole thing integrates out to pi. Okay, so are there questions or comments once we have the setup? Yes?
Right now, dz comes first, right? Is it ever possible for dz to come first?
Yes. So So all orders of dx and okay, yeah. Let's write this down. Goodbye, beautiful picture. Okay, so we can write dv in the order dx, dy, dz, or we can write it Okay, we can write it in any of the 6 possible orders. Okay, all 6 work, but you have to change the setup of the integral each time. So when you write down your region, these numbers here might change based on how these guys get switched. Okay, so we're going to do some practice with this idea of setting things up. Okay, I want to do another one of these domain sketches, and then we'll set up the domain, and then we'll check our work with the computer again. Okay, so here, oh yes, yep.
I was just going to ask, so is there something similar to like simple regions in 3?
Yes, great, yeah. So you can be simple in the x-coordinate, and that means you're bounded by a continuous surface on both sides. You can be, there's a perfectly analogous statement to simple. So. Okay, so yeah, there's a perfectly analogous statement about x simple regions, and here you're bounded by a continuous surface. And all that stuff about simple regions follows over to this context. Okay, so let's sketch the region of integration for this guy. It's important to pair up the variables correctly. So the outermost one is y, and that, or sorry, is x, and that tells us that 0 is less than x is less than 2. Now the next one tells us 0 is less than y is less than x. And the last one tells us in a statement here. Okay, so when we try and put the pieces together, we're going to have 2 slanted planes now. So let's try and draw what this thing looks like. And then we'll try and check our work with the computer. Okay, so the first condition is this one in x. X equals 2, x equals 0. Okay, the next condition will look a little bit funny in the picture we're drawing. So if this is the x-axis and this is the y-axis, then this line y equals x will sort of come out sort of like this. Okay, if we looked at this graph from above, we'd see the usual picture of y equals x. But because we're seeing it in perspective, it kind of creeps towards us. Okay, so this point of intersection is 2, 2, 0. Okay, and we're saying that y is bounded between y equals 0 and this line coming towards us. Okay, so that's the base of the region that we care about. We should also say where this point of intersection is. At 2, 0, 0. Okay, and now we have the really tough condition to draw in. This condition on z. So z is going to be sort of a sloping region. So where does z go? Z goes somewhere in here. We know the height above these two vertices. So above this vertex, we're going to go up to x plus y, which will be 2 plus 0. So this vertex will be 2, 0, 2. And then over here, we're going to go up a fair bit higher. Okay, above this vertex, we go to 2, 2, 4. Okay. And then this gives us kind of a domed roof. Okay, so we can imagine this kind of slanting roof over top of our green region. Okay, so we should get a kind of a wedge shape between two planes there. Okay, the slope along the line from here to the origin, that'll just be the line z is equal to x. And then along this line, it would be like z is equal to 2 times x. So there'll be less slope here than here. Okay, so it's hard to see what that shape looks like. Let's try plotting it. Okay, so we'll draw in the condition x is equal to 2. We'll draw in the condition y is equal to x. Okay, so that is the green wedge that we're seeing there. This green wedge is this small triangle here. One sec, I'm going to change the color of these planes. Right, so this small triangle is the base, and then our last guy is this slanting thing. In there. Okay, so the region we care about is underneath this red plane. Right? Underneath the red plane we have the triangle we've drawn, and when we put that red plane on top, it comes and fills in the space there. Okay. Yeah, so I recommend pulling these up on your computer and playing around with these sketches, because they're quite hard to see the region that we care about. We care about this guy just in here. It's kind of pyramid thing. Okay, so it's now 10 o'clock more or less. We're going to take a 10-minute break, and then we'll pick up with this bit about Fubini and changing orders. Okay, so let's pick up where we left off, and we'll keep going. So now I want to talk a little bit about changing order of integration for triple integrals. Okay, so let's take this guy and switch the order of integration and see what we get. Okay, so the first thing to do with these is to understand the order that you're given. So from the order that we're given, we get the following facts. We get 0 is less than x is less than 1. Then we get zero is less than y is less than x. And then we get this. Okay, so we read off from the bounds on the integral sign here how these variables relate to each other. And I want to point out they all fit together very nicely. So these guys all fit together in the form 0 is less than they fit together in this string of inequalities. Okay, and now we have to figure out what constraints would we have here, right? What bounds will we have on our integral for this question? So now we work from the outside in. We will look at the bounds on z first. The smallest that z can possibly get is 0, and the biggest that z can possibly get is 1. So we'll have those as our bounds for z. Okay, now we need to rewrite with dy coming next. So with dy coming next, we've got that y is sandwiched between z and 1. The smallest that y can be is z, and the biggest it can be is 1. Wow, the integral signs are just getting bigger and bigger. It's very strange. Okay, now our last variable here is x. X, the smallest x can be is y, and the biggest it can be is 1. Okay, so we always allow So when we're picking our bounds to rewrite, we allow each variable to be as large or as small as possible while satisfying old bounds. Okay, so notice that when we use this Fubini idea that we can change these around, the bounds change quite a bit, right? Here we've got, 0, z, y. Here we had 0, 0, 0. Okay, so things look quite a bit different when we change bounds of integration there. Okay, very good. So we rewrite the bounds, allowing each variable to get as big or as small as possible. Okay, now we're going to skip ahead a little bit and steal some material from next week that I think fits here better than it fits in next week. Okay, so one application of integration that I want to show is the idea of averages. Okay, so in a single variable, we have the following statement. Okay, and the interpretation of this is the average value of our function on this particular interval. Okay, so there's the single variable formulation of things. So now we have to think about the parts of this and say, what do they mean? So this part here is measuring a kind of a length. So we could say this is the length of that interval. Okay, and now if we want to move to multiple variables, we'll make a similar statement. So that the average should be the amount of area that we're running over times the value of the function. Okay. Okay, so I want to do like a sort of a mathematician thing and test a very simple example. Okay. Okay, so I want to find the average of something whose average we will already know and understand. So I'm going to pick my favorite number, 24, probably the best number, and we'll find the average of this over a rectangle. Okay, so what is the average of a constant function? What should it be? It should be the constant, right? If the thing's always outputting 24, the average really ought to be 24. So let's try that out. Okay, the area of that times d. Okay, so now we calculate out the two parts. Okay, so the area is length times width. So we get this expression here. Okay, we first integrate out the y. That gives us 48. Then we integrate out the x, and that gives us 48 times x. Multiply it out and get this. Okay, so we get 24 again. Okay, so the average of a constant should be that constant. All right, so this is good. If you go on to further math studies, you'll wind up doing a lot of examples kind of like this. You know, you write down a formula, you'll say, is this measuring the thing I want it to measure? And you wind up checking, very simple things. The average of a constant is that constant. Okay, very good. So that's one example of averages. Okay. Okay, so we want to find the average of e to the x plus y. Over this triangle with vertices 0, 0, 1, 0, 0, 1. Okay, so there's two parts to these calculations. We have to find an area and we have to find an integral. Okay, the region we care about is this guy here, right? So we calculate out the area. It'll be a half times the base times the height. Okay, and now we calculate out the average itself. So to calculate out one of these, we have to set it up as a simple region. So we go from 0 to 1 in the x direction, 0 to 1 minus x in the y direction. And we integrate that guy. Okay, we get our antiderivative. Plugging in the bounds into the fundamental theorem, we get this guy. When we evaluate we have the following confusing expression. We have e times x. Usually we have e to the power x. Now we get e times x. Okay, plugging in the bounds, we get e minus e minus e to the 0. So these e's cancel off. These guys give us a 1. Okay, so the total integral is 1. Okay, and putting the pieces together, right, we've got 1 over the area of the region times the integral, so we get 1 over a half times 1, so that the average in the end is 2. Okay, questions there, thoughts? Pretty nice calculation. I'm pleasantly surprised that it comes out to such a nice thing as just like 2. So there's no e's involved. Okay, so far in this course we've avoided talking about physics completely. I want to do just a little bit of a discussion of an application to physics that I think makes these three-dimensional integrals more reasonable. Okay, so our last topic for the day is going to be a bit of a discussion of mass and density, which will give us a concrete meaning for these triple integrals. So to start off, I want to ask sort of a very, very simple question. Okay, so suppose we've got these kind of blocks, and we know the weights of the blocks. Okay, let's say that these guys weigh 2 kilos, these guys weigh 1 kilo. Okay, then the very simple question is how much should the whole thing weigh? And we should add up these different weights. So how much does the whole thing weigh? Right, we add up the total and we get 6 kilos. Okay, that's one way of calculating out the weight of the thing. Another way of calculating out the weight of the thing is to think in terms of density. Okay, so density. So this is mass. We add up the masses. Another way to think of it is in terms of density. Okay, so here we're going, or I mean, we can think of it as weight by area or weight by volume. So here, these guys have density 2 kilograms per block, and these guys have density 1 kilogram per block. Okay, so if we do this in a sort of a density way, then we say that we have the following mass. We've got 2 kilograms per block times 2 blocks. Okay, and if we multiply these things out, the block units cancel, and we get 2 times 2 plus 2 times 1, and hopefully that's the same as before. And it is. Great. Okay, so if we think in terms of density, then we wind up with an application where we can use integrals. If we think in terms of weights, it's a little bit subtle. But if we think in terms of densities, we can integrate things. Because here we're adding up units per part times a number of parts. Okay, so okay, so suppose that we've got the following kind of density. Okay, how much does this thing weigh if it's got this if it's got this quadratically changing density? Okay, so the idea of this is that instead of this simple picture where we have discrete blocks, now we've got some kind of continuous picture where the density in the middle is quite low. But then going out towards the ends of the bar, the density gets higher. Okay, so we don't have discrete blocks anymore. We have a continuously changing density on this thing. But following through with this same idea of discrete blocks, we get the following formula. Okay, so I want to say what the units are here. This is kilograms per meter times a length, so times meters. Okay, so this thing measures a ratio of weight to length, and then this measures a length. Okay, so when we integrate out, these will cancel and we'll get kilograms. Okay, so what do we get? Okay, doing the arithmetic of the thing, we get 2/3 of a kilogram in weight. Okay, so that's sort of the one-dimensional version of these things. Okay, so we can do an analogous calculation in 2 dimensions. Okay, and coordinates. So we'll find its mass, same kind of setup as before. We're looking for the total weight of the thing. Okay, so we integrate out. Okay, now the units here should be the density should be weight per unit of area. And then we multiply that by dx. So that gives us a measurement of length times a measurement of length again. Okay, so let's go through the calculation. Paying attention to just x here. Right, we integrate out and get the following guy. And calculating things out here, we get a total weight of 8/3. Okay, so I want to come back to a question that was asked, very early on in the lecture. What does this stuff mean kind of physically? Or what's a way of handling these three-dimensional integrals? Okay, so to bring it back around to triple integrals, okay, we can think of this as a sort of a weight according to a particular density. Okay. The thing that I like about this interpretation is that we don't have to imagine four-dimensional space. Okay, we can imagine our 3D object, we can imagine our 3D region, and sort of imagine that certain parts of 3D space are like heavier than other parts, or they cost more, or something. Okay, so let's try out one of these. Oh, yes, just one last thing before we try it out. Volume winds up fitting into this picture very nicely. So volume is the weight if you have uniform density. Okay, so I just want to put that down somewhere. Okay, so that's kind of a nice way of fitting volume into this picture. Okay, so now I want to do a density calculation in 3D space. Okay, and Okay, so this is a situation where, you know, we've got this really sort of, this cube with a very odd sort of density on it. All right, up here where the coordinates are all 1, we have very high density up here. We've got density like E cubed, which is about 10. Okay, and then down here on the opposite vertex of the cube, we've got low density. Okay, so our density is not really uniform in this object. Okay, let's calculate it out. Okay, our bounds are all totally symmetric here. So we could put any order of integration we wanted, right? So because our bounds are all the same, we're a cube. Okay. Okay, now we get here. Right, so y occurs in both terms. It's got a positive number in front of it both times. Right, so we put in +1 both times, and now we put in -1. Okay, so what do we got? We've got 2 plus z minus e to the z minus e to the z plus e to the negative 2z. Okay. Okay, and I guess we've got a common term of e to the z floating around everywhere. So we might as well think of this as e to the z, e to the 2 minus 2 negative 1 to 1. Right, we can factor this e to the z out everywhere and make our function, a little bit nicer to integrate. Okay, so our resulting guy has this as its total weight. Okay. Are there questions about that calculation or any thoughts there? Nice. Okay. So I want to finish off the week like usual with a summary. Okay, so what do we sort of have in general from this week? What were our topics?
Density.
Density, yeah, sure. Yeah, let's play it backwards. Density, I guess averages. Okay, anything else? Yeah, triple integrals for sure. Okay, it was kind of implicit in what we were saying, but we also sort of had this triple integral Fubini thing again, that we can change order of integration. Okay, any other thoughts that come to mind? Topics for the week?
Sketching regions.
Yeah, sketching regions. Okay. Just as a bit of a warning, I find sketching regions super hard in 3D, so there probably won't be any on the exam. Okay, so it's just really hard to draw these things. Expect a 2D sketch though. Okay, there will be a 2D graphing thing. Okay, other topics, other thoughts from the week. Let's just rifle through the notes quickly. Density, sketching regions. Oh yeah, the min and max inequality. Yeah. Yeah, very good. Okay. Any other thoughts coming to people? Okay, I think that pretty much covers it. There's two things I want to make announcements for. So I emailed everyone asking for PDF notes. If you're taking PDF notes, that's awesome. Please send them in. I don't see any of the tablet people here today, but and if you used the LaTeX from the website, I would be curious just to look at your assignments, just to see how you use the LaTeX, how it could make it more user-friendly. So yeah, so PDF notes. Okay, and then the last announcement is tomorrow is the mock final. It's noon till 3 in this room. So please drop by, try it, attempt it. We won't be handing out copies in the usual way. If you want to like take a copy and just peace out, I recommend, it's not so good. Maybe just get one from the website. Please try and sit and write the thing. I don't want to give you guys a 5-hour exam in 3 hours, so I want to see how long it takes.